In this video, I'm going to give you an overview of the concepts of SLO script, which is part of the service level objectives for a next generation cloud framework. The SLOC framework is a research project that is jointly being developed by the Distributed Systems Group of TU Wien and FutureWay Technologies. To get started, let's briefly talk about SLAs and SLOs. So, service level agreements, or SLAs, in cloud computing define bounds within which a service has to operate. An SLA thereby consists of one or more service level objectives, or SLOs. An SLO is commonly defined as being a commitment to maintain a particular state of the service within a given period. Now this means that SLOs are always measurable. However, today they are often limited to simple capacity guarantees such as average CPU usage or memory usage or the response time of an API. Now this actually creates problems if you need to map your high-level business goals to the SLOs, because it's often quite difficult to map a high-level key performance indicator within a business strategy to low-level metrics such as CPU usage or memory, of course. So high-level SLOs would be much more suitable as business KPIs. Such a high-level SLO could be the cost efficiency of a service, which could relate the performance of a REST service, for example, to the total cost that you have to pay for that service. As part of our project, we want to make such high-level SLOs available to cloud customers. Let's now briefly take a look at the general process of checking an SLO and enforcing that SLO by using a very simple example, the CPU usage, but you could of course substitute a more complex SLO like the cost efficiency as well. So on the conceptual level, we always start out with one or more metrics which we can measure on the running system. So the CPU usage, or the memory usage, or the average response time of an API, and so on and so forth. You can of course also aggregate these metrics into more complex metrics. And these metrics then go into an SLO, which has some bounds defined by the customer. And the SLO evaluates if the application is currently operating within these bounds or not. If the SLO is violated, it triggers an elasticity strategy, which is supposed to ensure that the violation is corrected and that the SLO is respected again. Now, most commonly, the horizontal scaling strategy is used nowadays. So basically, horizontal scaling means that the number of instances of your application are either increased if the load is higher, or decreased if there is not so much load. But there are other elasticity strategies as well, such as vertical scaling, which increases or decreases the resources of a single instance, or combinations of horizontal and vertical, and even more complex things. What we see commonly in production use today is monitoring of very simple parameters, such as the CPU usage. And this is then fed into, for example, an average CPU SLO, which is tightly coupled to an elasticity strategy. So in this case, horizontal scaling. Now this means that if we, for example, want to change the average CPU SLO for something else, then we usually need to change this whole controller here because the SLO is tightly coupled with the elasticity strategy. There are now some solutions that are coming up which are currently in beta stage, which allow the introduction of custom metrics, but still the SLO is often very tightly coupled with a particular elasticity strategy. And with SLO script, we want to tackle this problem. So we want to make sure that we get rid of this surrounding box and this hard link here so that you can have a very loose coupling between SLO and the elasticity strategy. So if you want, you can take a different SLO, such as cost efficiency, and plug that one into the horizontal elasticity strategy. Or you can take either of these SLOs and plug them into a vertical elasticity strategy, or a combination of these two. So this basically greatly increases the flexibility of the system and allows far more SLO and elasticity strategy combinations. SLO script is a TypeScript-based language and framework. It has type safety features which ensure the compatibility between the workloads that you apply the SLOs to, the SLOs themselves, and the elasticity strategies. We will get to that in a couple of minutes. But let me just briefly say, this ensures that you can apply an SLO only to an application which is supported by that SLO. So for example, if you have an SLO that's tailored for REST services, you will not be able to apply that SLO to a SQL database which doesn't even offer a REST interface. SLO script, as I previously mentioned, features decoupling of SLOs from elasticity strategies, which promotes reuse and increases the number of possible SLO and elasticity strategy combinations. And the whole thing is orchestrator independent in order to promote extensibility. So there is a completely independent core, and then we use adapter libraries to plug SLO script into a particular orchestrator. So right now, for example, we support the Kubernetes orchestrator, so we have an adapter library for that one. But you could, of course, also add an adapter library, for example, for OpenStack. So how do you apply an SLO to a target workload, target deployment? So let's say that I have an application deployed in my cloud account. This is the target deployment. I want to connect it to this elasticity strategy, and I've picked a certain SLO that I want to use. Now these entities, as you can see, they are independent from each other. So we need to find a way to connect them. For this purpose, we use what we call an SLO mapping. The SLO mapping allows you to configure an SLO, so define the bounds that you want to have, and apply this SLO to your target deployment, and also at the same time establish a relationship to the elasticity strategy that you use. So the SLO mapping is the glue between all of these components, which actually makes the SLO enforcement work. Okay, I previously mentioned that one of the features of SLO script is type safety. So by that we mean that, for example, if you have an SLO which is specifically tailored for REST services. So it could determine the cost efficiency of REST service. Then our type safety feature ensures that you cannot inadvertently apply this SLO to, for example, a SQL database which doesn't even offer a REST interface. Just wouldn't make sense. At runtime, it would trigger an error, which might be hard to find. So what we make sure is that you see this problem already as you are configuring the SLO, and we don't even allow you to apply this incorrect configuration. So we have the service level objective here, which defines a certain type of input configuration, here as indicated by the yellow color. So the colors in this diagram always represent certain types. So the yellow SLO configuration in turn defines a certain type of target that you can apply it to, indicated by the orange color, which in this case would be a REST service, which means if you try to put another thing here, such as a website application or a database application which offers no REST interface, you wouldn't be able to do that because the types would not match. Then on the other side, the SLO of course produces some output, indicated by the blue color. The SLO output is of course necessary as input to the elasticity strategy. So an elasticity strategy of course requires some configuration on its own, here symbolized by the violet color. And the elasticity strategy configuration expects a certain type of output from the SLO. So as you can see, the blue SLO output establishes the link between the service level objective and the elasticity strategy. So what is an SLO output? For example, a generic SLO output could be a percentage of SLO compliance. How much does my workload currently comply to the SLO? And if we have this type of SLO output, then we can use the SLO with any elasticity strategy that supports this SLO compliance value as input. Of course, you can have different types of SLO outputs. So if you have an SLO that's specific to a very complex application, you might want to store additional parameters in the output and create a new SLO output type for that. And this would then, of course, only be usable with elasticity strategies that support this as input, which, since the application is a very complex one, makes perfect sense because the elasticity strategy needs to take into account how this application can be scaled. But the goal is, of course, to use generic SLO output types as much as possible so as to allow as many SLOs as possible to be used with as many elasticity strategies as possible. Our project was designed to be extensible from the beginning onwards. So we came up with a plugin mechanism which allows cloud providers to basically define packages of SLOs that they support, and they can package them up in a plugin and then offer them to their customers, or even sell them to other cloud providers if they are using a similar system. So SLO plugins basically encapsulate all the logic that's contained in an SLO and can also be used to hide intellectual property. So how do you develop an SLO plugin? As the cloud provider or service provider, you just set up a TypeScript project and use our SLO script libraries to develop the SLO. So for example, here we have the cost efficiency, consists of TypeScript code. And then this is fed into a preprocessor, which will build an executable, which will build a container image containing an executable SLO controller that can be run inside the Kubernetes orchestrator. This will contain our generic SLOC runtime and, of course, the cost efficiency SLO. And that whole thing, together with some configuration files, can be packaged up as a plugin and then finally deployed to the Kubernetes orchestrator. I'd like to note here, since this project is still under development, the automatic preprocessor doesn't exist yet. So right now, you have to compile the TypeScript project manually and package it up into a container image manually and deploy it manually to the orchestrator. But in the end, of course, packaging will be done automatically. Okay, next up, we have a little demo of our cost efficiency SLO for REST APIs, which we apply to a deployment of the open source headless CMS Gentix Mesh. The cost efficiency basically takes multiple metrics as input. We have the requests per second, which are faster than a certain threshold. We have the total requests per second, and we have the total cost of the deployment. And we connect the cost efficiency SLO to a horizontal elasticity strategy. In the demo, we'll first give you an overview of how we have deployed our CMS. Then we'll take a look at how the service provider can define a new SLO. Next, we'll show you how the service consumer or the customer actually configures and applies an SLO. Then we'll give you a quick glimpse at the upcoming SLOC user interface. And finally, we'll run a little load test and see the SLO and the elasticity strategy in action. Okay, so to get started with our demo, let's first take a look at the workload that we have deployed in our Kubernetes cluster. As I previously mentioned, we're using the open source headless content management system Gentix Mesh for this demo. So we have a namespace called Mesh, and then we have two stateful sets in here. One is the CMS itself, with currently having two pods, and then we have a distinct stateful set for Elasticsearch. Before applying our cost efficiency SLO, let's take a very brief look at the implementation of the SLO itself. That's of course also done with SLO script. So it consists mostly of a TypeScript class, which implements the service level objective interface. That interface supports three generic type parameters. The first one describes the type of input that the SLO requires, so its configuration data type. The second one describes the type of output data that is produced by the SLO, and this must of course match the input data type of the elasticity strategy. And the third parameter, which is optional, can be used to limit the types of workloads to which the SLO can be applied. So as you can see, the implementation of this complex SLO is not so simple, which actually proves that that it's very useful to have a high-level language which provides high-level abstractions in order to keep this SLO maintainable. So just as a quick side note, here we have some metrics queries which would normally be expressed in the query language of the used time series database, but we have decided to create an independent abstraction layer here as well. So we have our own metrics query API, which is object-oriented and type-safe and can be used with multiple time series databases. Currently, we ship an adapter for Prometheus, but in the future, adapters for other time series databases, like for example InfluxDB, can be added as well. So this SLO controller needs to be compiled and packaged in an SLO plugin and then deployed to the cluster. So this is all done by the service provider, so the customer doesn't need to bother about this. Once the controller is deployed, the customer can configure the SLO on his workloads. And to do that, we will create an SLO mapping, which is just a TypeScript object. So inside this TypeScript file, we import some SLOC types and then create a default export of type cost efficiency SLO mapping. We add some metadata. Namespace has to be the same as the one where we deployed the stateful sets, and then the name can be whatever we want, because that's just the name of the SLO mapping. The spec property contains the actual configuration of the SLO mapping. So here you can immediately see the big benefit that's provided by the strong typing. So since we're using TypeScript as a base, you get immediate compatibility with the code completion features of that language, so you can explore the properties which you can set on this SLO mapping, and you can also see which types you can use for that. So first we create a target ref, so we tell our SLO to which deployment we want it to refer. So I'm just quickly going to type that. If these names, group version, kind, and so on, seem familiar to you from the Kubernetes world, in fact, our object model is heavily inspired by the Kubernetes object model, but it's not the same. So there are some differences. Also, our object model is designed to be orchestrator independent, so we provide a transformation service which actually transforms this into Kubernetes objects, and this can be done for other orchestrators as well. So now we have to pick an elasticity strategy. We said that we were going to pick the horizontal elasticity strategy, and now we need to provide some configuration for the SLO. Response time threshold, we'll pick 500 milliseconds here, and a target cost efficiency. Okay, we would be good to go now and ready to deploy that SLO. However, first I would like to show you some of the benefits of the strong typing feature. So for example, if we wanted to use a different elasticity strategy, here we could of course pick a different one here as well. And if we use, for example, this one here, it's just a mocked one, the DB specific elasticity strategy, which would only be compatible with SQL databases, but not with our REST services, that we want to apply it on, we would immediately see that there's an error in the code, that the types are incompatible, which is because the DB-specific elasticity strategy expects a different kind of input than our cost efficiency SLO provides. So this is an error that in many cases would only be revealed once you applied your configuration to the cluster, or once you or tried to run everything. But with SLO script, you actually see the error right at the time of writing, and you can immediately correct it. So now let's quickly build this serializer that we have. This is a step that right now unfortunately needs to be done because we don't have the automatic controllers yet, which will in the future take the TypeScript code and directly apply it to the cluster. So right now this needs to be done manually. But it can also be used to show you how the serialization works. So the TypeScript object that you saw has been converted to that YAML, and we can just pipe that into kubectl apply in order to apply that to our cluster. You can see that the cost efficiency SLO mapping has been created now. Here we're running our SLO controller locally. We can now see the output that's produced by the SLO controller. It has already detected that we've added a new SLO mapping, and every 20 seconds that mapping will be evaluated. So we should soon see the output, and here we are. So currently the SLO compliance is 100%, so no scaling needs to be done. Of course, because there is no load right now. But in order to make this a little more fun, we will now generate some load on our CMS. So I'm gonna spin up a load generator. And while that is starting with load generation, let's quickly take a look at the user interface that will be shipped with SLOC. In the end, there will be a web user interface which will allow you to have an overview of all the plugins that are deployed, the available metrics, the available SLOs, the SLO mappings, and various graph visualizations. Most of that is still to come right now. At the moment, we only have the visualization part. So here we take graphs provided by our Grafana instance and display them here. And you can see that the load has already gone up since we started the load test. If we take a look at our SLO controller, you can see that the SLO compliance percentage has gone way up, which means since it's over 100, we need to scale out. And in fact, this has already arrived at the Kubernetes cluster. So the stateful set has been configured now to scale out to 3 pods. And if the SLO compliance continues to stay high, this can be expanded further, of course. So with that, I would like to thank you for watching this demo video. And if you have any questions, then please reach out to us.